I am Taryn Hatcher, and this is our final group project. We are Group 4, and the members are myself, Taryn Hatcher, Miranda Gellinger, and Lindsay Obron. We are going to be talking about topics from Chapter 13, which is non-parametric statistics. First, we are going to cover the sign test, and I will be doing this. Next, Miranda will talk to you about the Wilcoxon rank sum test and the Wilcoxon sign rank test. And then after Miranda, Lindsay will cover the Kruskal-Wallis test and the Spearman rank correlation coefficient and the runs test. So first, let's begin with the sign test. First, we're going to cover the single sample sign test. The sign test for single samples is the simplest non-parametric test. It is used to test the value of the median for a specific sample. When using the sign test, the researcher hypothesizes the specific value for the median of the population. The researcher also selects a sample of data and compares each value with the conjectured median. Then the researcher assigns a plus sign if the data value is above the conjectured median. The researcher could also assign a minus sign if the data value is below the conjectured median. And the researcher assigns a 0 if the value is exactly the same as the conjectured median. Next, the numbers of plus and minus signs are compared. If the null hypothesis is true, the number of plus signs should be approximately equal to the number of minus signs. If the null hypothesis is not true, there will be a disproportionate number of plus or minus signs. Test value for the sign test is the smaller number of plus or minus signs. So here's our first example. Weekly earnings of women. According to the Women's Bureau of the U.S. Department of Labor, the occupation with the highest median weekly earnings among women is pharmacist, with median weekly earnings of $1,603. Based on the weekly earnings listed below from a sample of female pharmacists, can it be concluded that the median is less than $1,603? And we're going to use, I'm just going to call it A here because I don't have the symbol. A equals 0.05. So here is our data set. So let's begin. Step 1, we're going to state the hypothesis and identify the claim. So the null hypothesis is that the median equals, you can put the dollar sign here, you don't have to though, $1,603. The alternative hypothesis or the claim is that the median does not equal $1,603. All right, claim right here. Okay, now for step 2, we are going to find the critical value. Critical value is where you compare each value of the data with the median. If the value is greater than the median, replace the value with a plus sign. If it is less than the median, replace it with a minus sign. And if it is equal to the median, you replace it with a 0. So we're going to look at our table right here. 1550 is less than 1603. 1430 is less than. 2465 is greater than. 1429 is less than. And 1217 is less than. 1355 is less than. 1570 is less than. 1655 is greater than. 1829 is greater than. And 1501 is less than. 1777 is greater than. 1701 is greater than. 1484 is less than. 1812 greater than. And the last one, 1449, less than. So here are all of our signs, and you see that we did not have any zeros because there was not a number that represented 1603. So this is where we find the critical value. So let's count our data set, or our sample size, which is n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So n equals 15. Now we're going to need to go to a chart in the back of our book. I have it here on the PowerPoint. So we said that A equals 0.05. This is a two-tailed test, and n equals 15. So it's going to meet at about right here. So this is our critical value, 3. So I'll put it right here. Just put CV equals 3. Alright, so now we have found our critical value. Step 3 is where we compute the test value. You count the number of plus and minus signs obtained in step 2 and use the smaller value of the test value. Okay? So there are 1, 2, 3, 4, 5, 6 plus signs, and 1, 2, 3, 4, 5, 6, 7, 8, 9 minus signs. So 6 is our test value. So I'll put TV right here equals 6. Now on to step 4. This is where we make the decision. We're going to compare the test value with the critical value. If the test value is less than or equal to the critical value, the null hypothesis is rejected. If the test value is greater than the critical value, the null hypothesis is not rejected. So we take 6 is greater than 3. Therefore, we do not reject the hypothesis because there is not enough evidence to reject the claim that the median is less than $1,603. That completes that problem. Let me just erase a few things and then we'll get back to the PowerPoint. Alright. Oh, also in addition I wanted to add this in here. When the sample size is 26 or more, the normal approximation can be used to find the test value. The formula is given below. Z equals x plus 0.5. I'm sorry, there's a typo in the above section. Just ignore that is. Back to here. Z equals x plus 0.5 minus n divided by 2. And this is all over the square root of n divided by 2. Okay, now let's talk about paired sample sign test. The sign test can also be used to test sample means in a comparison of two dependent samples, such as before and after test. Here's our example for this one. Routine maintenance and defective parts. A manufacturer believes that if routine maintenance, cleaning and oiling of machines, is increased to once a day rather than once a week, the number of defective parts produced by the machines will decrease. 9 machines are selected and the number of defective parts produced over a 24-hour operating period is counted. Maintenance is then increased to once a day for a week, and the number of the defective parts each machine produces is again counted over a 24-hour operating period. The data are shown here. At A equals 0.01, can the manufacturer conclude that increased maintenance reduces the number of defective parts manufactured by the machine? Now back over here to the board. Step 1, again, is to state the hypothesis and identify the claim. The null hypothesis is that increased maintenance does not reduce the number of defective parts. I'm going to take a second to write this here. I'll just shorten it at that. The alternative hypothesis is increased maintenance reduces the number of defective parts. now we have our hypotheses, and we're going to move on to step 2, which is again find the critical value. This is where you subtract the after values from the before values and indicate the difference by a positive or negative sign or a 0. So, if we subtract 5 from 6, that leaves us with a positive number. If we subtract 16 from 18, that leaves us with a positive. 7 from 5, a negative. 4 from 4, 0. 18 from 16, negative. 12 from 13 is a positive. 14 from 20 is a positive. 7 from 9 is a positive. And 1 from 3 is a positive. So now we have all of our signs, and this time we do have 1 0. But we're going to kind of throw it out to get our sample size. So to get the sample size, you just count the signs. 1, 2, 3, 4, 5, 6, 7, 8. So our sample size is 8, and we are doing this at A equals 0.01. Let me go to the chart that's in the back of our book. So this again is going to be the two-tailed test, but now we're in this column with the 0.01, and you are again up there at the top where the 8 is. So this is telling us that our critical value is 0. So I'll write CV equals 0. Okay, now on to step 3. This is where we compute the test value. You count the number of positive and negative signs found in step 2 and use the smaller value as the test value. So clearly this looks like the lesser of the signs. There are 2 minus signs. So 2 is going to be used as our test value. Now moving on to step 4. Step 4 is where we make the decision to compare the test value with the critical value. The test value was 2, and 2, I'll just circle these, 2 is greater than the critical value, which is 0. Therefore, we do not reject the hypothesis because there is insufficient evidence to prove that the increase in maintenance reduces the number of defective parts. This concludes the section on the sign test. Now you are about to see Miranda in the next video.
Alright, today we're going to be talking about our Wilcoxon rank sum test and the Wilcoxon signed rank test. I'm Miranda. I'll be telling you how to do all this. Back to our slideshow. So we'll go on to our next slide. These are the formulas we're going to be using for that first rank sum test. But first we're going to go over real quick about both tests. The rank sum test is used for independent samples, while the sign rank test is used for dependent samples, and both are used to compare distributions. For both tests, the values of the data are samples, and then you combine them and then you rank them. If the null hypothesis is true and there is no difference in the population distributions, then the values in each of the samples should be ranked, approximately the same. If there's a big difference in the sums of the ranks, though, then the distributions won't be identical and the null hypothesis will need to be rejected. Okay, for the Wilkins rank sum test, we're back to that. For the first step, we're going to state our hypothesis and identify the claim. Step 2, we'll find the critical value, and you're going to do that using table E from the book. Step 3, we compute the test values, and this will all become more clear when we do our sampler problem. You're going to combine the data from the 2 samples, and you're going to arrange that combined data in order and then rank each value. Then you're going to sum the ranks of the group with a smaller sample size. If both the groups have the same sample size, either one can be used. It doesn't really matter which one you pick. then we're going to use the formulas to find the test value. And these formulas right over here, in case you forgot them. And then we're going to make our decision, and then we'll summarize our results. And here's our practice problem, if you just want to take a second to glance that over. Alright, so first we're going to state the hypothesis and identify the claim. So for our null hypothesis, there is no difference in the lifetimes of the two brands of handheld games. And for our alternative hypothesis, there is a difference in the lifetimes of the two brands of handheld video games. Step 2, we're just going to find our critical value, and we'll do that using table E. It's plus or minus 2.58, and since it's a two-tailed test, that's why there's the plus and the minus. And next we're going to compute our test value. So we're going to combine the data from the two samples, and we're going to arrange that data in order and rank each value. And make sure you are indicating which brand it is, otherwise you'll just have a mess of numbers. So here it is. It starts with our lifetimes being the highest, and then works all the way down to the lowest. And then there, as you can see, everything is ranked. Okay, then we'll sum the ranks of the groups with the smaller sample size. And this one happened to have the same sample size for each of them, so I just chose group B. I added all of that together as 112.5. And then we just start substituting into the formulas to find that test value. Not too complicated, just plugging some numbers in. So Z ends up being negative 0.9192. So then we have to make our decision. And our decision is to not reject the null hypothesis because negative 0.9192 is greater than the negative 2.58. So then we just summarize our results, and there's not enough evidence to reject the claim that there's no difference in the lifetimes of the two brands of handheld games, and researchers should not conclude that there is a difference in the lifetimes for these two brands. So now we'll go back to our slideshow and move on to the next test. So the sign rank test. Step 1 is once again just stating your hypothesis and identifying the claims. And then you find the critical value, and this time it'll be from table K. Next, we're going to compute the test value. And first we're going to make a table. And once again, this will be more clear once we do our sample problem. And then we're going to find the difference of the before and afters and place those values in the difference column. And then we're going to find the absolute value of each difference and place that in the absolute value column. We'll rank each absolute value from lowest to highest and place the rankings in the rank column. We'll give each rank a positive or negative sign according to the sign that it was when we first figured out its differences. And once it's in a table, it'll be much easier to see. And then we find the sum of the positive ranks and the sum of the negative ranks, and you make sure to do that separately. And then we're going to select the smaller of the absolute values of the sums and use these absolute values as the test value. And step 4 is to make the decision. We'll reject the null hypothesis if the test value is less than or equal to the critical value. And step 5 is just summarize the results. So just a quick back look at all of our steps. Oop, little too zoomed in for you there. Alright, and then here's our practice problem if you want to take a quick look at that. Alright, so we go to our first step, and it's to state the hypothesis and identify the claim. So our null hypothesis is there is no difference in healthy or in weight after a new healthy diet, and then our alternative is that there is a difference. Then we're going to find that critical value, and we're going to be using table K for that. And since the population size is 8, this two-tailed test, the critical value is 4 for us. Okay, then we're going to work on finding our test value. We're going to make a table, like I talked about before, so things should be a little more clear now. There's your before, after, the difference column I talked about, absolute value column, rank, and signed rank. So we'll find our differences, just subtracting before minus after, and we'll place those in the difference column. So there's just our simple subtraction. Then we're going to find the absolute value of each of those differences and place those results in the absolute value in the table above. So all of those, as you can see, are positive because the absolute value doesn't keep the negatives. Okay, and then we're going to rank each absolute value from lowest to highest and place the rankings in the rank column. In the case of a tie, assign the values that rank plus 0.5. So there's our data, and it's all ranked. And then we're going to give each rank a plus or minus sign according to the sign and difference. So if it was negative before, like our first one, then it'll be negative in its signed rank column. And there's our table all completed. And then we're going to find the sum of the positive ranks and the sum of the negative ranks separately. So there's that, 31 and negative 5. And we'll select the smaller of the absolute values, obviously. That's going to be the negative 5. And we use the absolute value as the test value, so it turns into the 5 for us. Then we'll make our decision, and we'll reject the null hypothesis if the test value is less than or equal to the critical. In this case, 5 is obviously larger than 4, so we'll have the decision to not reject the null hypothesis. And then we just summarize our results. That there is not enough evidence to support the claim that there's a difference in weight after a new healthy diet. So hopefully this is all cleared up for you now.
For this portion of the video, we will be going over the Kruskal-Wallis test. This test is used when the assumptions for the ANOVA test that the populations are normally distributed and that the population variances are equal cannot be met. The Kruskal-Wallis test, sometimes referred to as the H-test, can be used to compare 3 or more means. For this test, the sample size must be 5 or greater. The degrees of freedom are going to be equal to k minus 1, with k being equal to the number of groups. For this test, you first rank all data values as a group and then separate them when you then compute these values using the H formula. This formula estimates the variances. If the samples are from different populations, the ranks will be different and the H value large, leading to a rejection of the null hypothesis. If the H value is small, the hypothesis will not be rejected. This test is always right-tailed, and the chi-square table should be used to find the critical values. The formula will be given in the following PowerPoint, followed by an example. For this example, a principal would like to know if the reading scores for her school are consistent across 3 third-grade classrooms. A 95% confidence interval will be used. We will first group the data as 1 and then rank it 1 through 15 because there are 15 total data points, 3 sets of 5. The totals for Group A will be 30, Group B will be 48, and Group C will be 43. We'll then input this into the formula, finding the total to be 2.53, which is lower than the critical value of 9.48. Therefore, we will not reject the null hypothesis. This is an overview of the Spearman rank correlation coefficient and the Run's test. Spearman rank correlation coefficient may be used when the requirements for the Pearson coefficient cannot be met. For this test, the difference in ranks is found and R sub 0 is computed by using these differences. If both sets have the same rank, R sub S will be +1. If it is the opposite, R sub S will be -1. If there is no relationship, R sub S will be 0. The formula for R sub S is equal to 1 minus 6 times the sum of the differences of the rank squared over the number of the data pairs times the number of the data pairs squared minus 1. We're going to go over a quick example, and this will be shown in the following PowerPoint clips. For this example, we will be trying to find if there is a relationship between the subgroups A and B for the sets at 95% confidence interval. We will use the L table to find the critical value, which is going to be equal to 0.738. Rank each data set, letting x1 be ranking for A and x2 be ranking for B. Then subtract x1 minus x2 to find the difference. Finally, squaring the difference and finding the sum of the squares. Input these values into the R sub S formula and either reject or do not reject the null hypothesis based on the value compared to the critical value. If the value you find is less than the critical value, you will not reject the null hypothesis. If the value is higher than the critical value, you will reject the null hypothesis. The next test we'll be covering is the runs test. The runs test determines if a sample has been selected at random. A run is the succession of identical letters preceded or followed by a different letter or no letter at all, which would be the beginning and the end of the grouping. The test for randomness considers the numbers of runs rather than the frequency the letters occur. If a data is selected at random, there should not be too few runs or too many runs. To determine whether the number of runs is within the random range, use the critical value for the number of the runs chart. For an example, we will be finding if the number of men and female entering a building is random. The set will be MMMF, MMFF, MMMFFF, with M equaling male and F equaling female. This will also be covered in the PowerPoint slides followed. The total of runs is 6, with the total number of men being 8 and the number of females being 6. If you look at the chart, the number that is acceptable is a range of 3 to 12. If we input the values into the formula, we will find that 6 is our answer, and since 6 is between 3 and 12, we will choose to not reject the null hypothesis.
This concludes Group 4's overview of the topics covered in Chapter 13, Non-Parametric Statistics. Thank you for watching, and I hope you enjoyed it.